Hello and welcome back to OpShin Pioneer Program week 3, lecture 2. And in this lecture we will look at time. Time in smart contracts is a bit delicate, as I have explained in the last lecture, where we noticed that actually a smart contract does not know the exact time at which it is spent, but only the range of possible times that it could be spent at. And so in this lecture we will look a bit more into how this works in practice. How do we work with these intervals? Why do we have the intervals? Again, a recap of I just quickly mentioned this last lecture. We have the validity intervals because at the time of constructing the transaction, we are constructing it. We are not submitting it to the chain. So we don't actually know yet at what time it will be really published on the chain and included in the transaction history. At the same time, we want to have a deterministic construction of the transaction. So we want to make sure that if during constructing our transaction it correctly works out, then also when later submitting it to the chain, it will correctly work out. In a sense that it will not suddenly fail because the time that it was published was different than the time we expect than the time when we constructed the transaction. So what Cardano provides as a solution is this time range. Instead of saying, instead of looking at the current time, we just say, okay, we know our transaction is valid in a specific time frame, and it has to be valid in the entire time frame because it doesn't know any specific point of time in this time frame. It just knows, okay, this is the time frame. Anywhere in there I could be published, and then you validate whether that's okay for you. So that's what the smart contract does, and what the node does is it checks that you can specify slots, a minimum and a maximum slot for publishing your smart contract, publishing your transaction, and if the transaction falls outside of the slot, then the node will immediately discard the transaction. So this is a very cheap check, and so you avoid the high cost of trying to evaluate the smart contract, then realizing it's wrong, and then taxing the user for this evaluation. Instead, you just look at the time range. If the time range doesn't match, it gets discarded. And if the time range is valid, then you execute the smart contract, and there really no surprises should happen because the time range was already fixed when you built the transaction. There are some caveats here. One is that the Cardano consensus protocol operates on slots, which is also how you define the validity range of your transaction. In the same time, Pluto scripts use real time. So as you might have noticed, these time ranges are denoted as POSIX time. And actually what we have here is Unix epoch, which means seconds since 1st of January 1970, and they are in milliseconds. This is important to notice if you usually work on Linux or you have some experience with Unix timestamps. They're usually in seconds, but what we are working with is milliseconds since 1st of January 1970. And this is distinct from the slots that you use in Cardano. So don't expect to be able to work extremely precisely with this, because you will just specify the time range in slots towards the node, and then it will be translated by the node into Unix epoch time and then execute the smart contract with that. Then there is a second caveat. because you specify the time in slot length in the transaction, but the slot length is actually not indefinitely fixed. Currently it's 1 second, but it used to be 20 seconds, and it could be changed to any other value. So this is why transactions are generally not allowed to specify a future time in a slot that's too far into the future. Typically, the maximum is 36 hours. So yeah, you cannot. You might get some error like horizon out of bounds error or so, and this is because the transaction you built has a future validity that's too far in the future, so we cannot guarantee that actually slot lengths will have the same meaning so far in the future, so we don't allow constructing this transaction. Okay, so finally, how do these intervals look when we look at them in Plutus? This is the general definition of the POSIX time range. There's a lower bound and there's an upper bound. And we can have a closer look on how this is implemented specifically. You can always just go look at contract and then control and click on definitions of a datum, and then it will take you to the definition in the option code. And most of the option code that you import is actually also valid option code itself, so there should be no surprises here when you look at stuff. It's defined in the same way that you would define things. It's just already done for you as a kind of standard library. So let's have a look at transaction info, then the validity range. There's upper bound and lower bound. And both of these, they actually look extremely similar. They just have different names. Have a limit and information on whether they are closed or not, which means they could be closed in the sense that the last second of the range could be part of the contract or not, part of the validity or not. It's unlikely that you will ever need this because it's milliseconds, and precision on this level will probably be way more precise than you can actually handle, but it's included anyways. You can mostly ignore this though, and it's just necessary to define, so we can define later some operations on comparing bounds. Now the limit is more interesting. This could be either negative infinity, could be a finite POSIX time, or a positive infinity. So negative infinity and positive infinity are both don't have any fields. They're just supposedly there. They're not actual values. They're negative and positive, and we need to define comparisons separately for these values. And then there's finite POSIX time. It just contains a POSIX time field, and POSIX time is just an integer. So validity range has an lower and upper bound, which have a limit and information whether they're closed or open. And then the limit itself could be negative infinity, positive infinity, or a finite time. And note that this can actually be the case for both upper and lower bound. So if you so the upper bound is the latest time at which your transaction is valid, and the lower bound is the earliest time at which your transaction is valid. So if you set the lower bound to negative infinity and the upper bound to positive infinity, then your transaction is always valid. If you set the upper bound to negative infinity, you can think for this yourself for a second, then you will have a transaction that's never valid, right? Because the latest it's valid is negative infinity. It will never be valid. And the same, If you set the lower bound to positive infinity, then it will never become a valid transaction. But usually what you have is either both bounds a finite POSIX time, like a minute in the future and a minute in the past, or from the time of constructing the transaction, or you have like an upper bound but no lower bound, or a negative infinity lower bound, or a positive infinity upper bound and a negative lower bound, and a finite lower bound. So yeah, we will do a short hands-on example for this by just looking at the basics for our vesting contract. And actually, what you can do in Python is you can just spawn an interactive shell, and this will create a shell for you. Make sure that you are in the poetry shell. So just to be sure, you can run poetry shell first, and then let's actually go into week 3, but it shouldn't really make a difference. And then we can call Python here. Let me move myself. I can see this. Okay. So I'll just clear and then Python 3. So what you can do, because all of OpShin code is also for the Python code, we can just play around in the Python console to get a bit of a feeling what's happening. So we can do from opshin.ledger import interval, and now we have interval in our scope. Actually, we should rather import interval, import everything from interval. Now we have, for example, the function make range in scope. And if we call make range from -3 to 2, for example, make range, then you see it will construct this whole complex data structure for us. So here we are also actually doing the same from option ledger interval import everything. And what you get is when we look at make range, you see it recursively constructs, it just takes 2 integers, then it constructs lower bound, constructs a finite POSIX time, sets the lower bound, and just sets the bounds to true, because we usually don't care about whether or not something is closed. So yeah, here you can see exactly this. It's a POSIX time range, the lower bound is set to finite -3, and the upper bound is set to finite 2. And there's also, for example, make 2, which will construct a lower bound of negative infinity and an upper bound of the time that we specified. So this will construct a validity range that is up to a specific point, but indefinite in the negative. So infinitely large. And let's say our transaction is valid from timestamp from 1 millisecond to 6 milliseconds in the future. Make range. This is the range. And now let's say we set a deadline, and that's from any time up until 7 milliseconds. And now we can use the function contains. This checks that the deadline contains, this is a range, a time range, right? And we just check that this deadline contains the validity range of the transaction. And this is in this case actually true, because 1 to 6 is contained in 7 to infinity. But if we, for example, make a time range of 3, make 2, 3, that's the deadline. After 3 milliseconds is our deadline already. And then we check containment. Then it's actually not the case, because if the transaction is valid from 1 to 6, and it should have been submitted before 3, then there's a time frame from 3 to 6 where the transaction could be submitted, but it's actually not valid. So this is what we expect. We don't want contains to pass here. So yeah, feel free to play around a bit more, have a look at the functions in the ledger interval definitions. There's more information, for example, on how to directly compare the lower bounds and upper bounds, there's some transformation between bool data and the built-in bools that we are using mostly in OpShin, and so on. Right, see you in the next lecture, where we will look at a concrete contract that makes use of these interval values.